Welcome to the Gridwise Architecture Council's video library. The following presentation by Aikin, CEO of Dynamic Grid, is entitled High Performance Battery Applications Using Lithium Titanium Oxide and was presented to the Gridwise Architecture Council on March 18, 2026. Welcome, Kay.
I see that. I'm going to go to slideshow.
Yep, I see your desktop is almost as cluttered as mine.
Is that good? Yeah, mine's very cluttered.
Yep, looks good.
All right. So I'll go here. So we started out in 2010. Some of you know Dr. Carol Johnson, who's my partner. We started a company called Introspective Systems, and we were doing deep tech science work, mostly for the U.S. government. Think U.S. Geological Survey, Department of Energy, DARPA, U.S. Air Force. One of our flagship products is we locate all the world's earthquakes in real time for the U.S. Geological Survey. So we provide the core algorithms for in Golden, Colorado, running in their server farms, and collect about data from about 20,000 sensors worldwide, petabytes of data daily, and process that to locate earthquakes. Version of that also works in the UN for the Comprehensive Test Ban Treaty Organization, and also for the 25th Air Force in Patrick Air Force Base in Florida. About 8 years ago now, we got an opportunity from Chris Irwin, who is our sponsor, to provide an overview of grid architecture from non-grid people per se, though my background is energy engineering. And that got us started on what is now Dynamic Grid. We're based in Portland, Maine. We're focused on the production right now of energy storage systems combined with advanced energy controls for C&I customers. And why is it not going? There we go. So presentation is what our new product is, and our plant that we're building currently in Lewiston, Maine, is high performance battery applications using lithium titanium oxide. So one of the problems, we're focusing on the commercial and industrial market. One of the problems in the battery world is most of the manufacturers coming out of China are aimed toward grid scale, and these are 4 or 5 megawatt hour battery blocks, and those sizes don't work very well. There's a couple of manufacturers, Generac, that produce 250, 500s, but basically they are very commoditized and products. So we've designed a very, very flexible system architecture that allows us to independently change both the power side of the equation as well as the energy storage side of the equation. We also integrate our microgrid, and hopefully, if we get deployed someday, our DERMS controls into those boxes, into the containers. And we're also finding in design world, there's a lot of system design failures, and a lot of that is combination of not understanding degradation, exactly how batteries degrade, their round trip efficiencies degrade over time, et cetera, and we find failures in actual performance, because customers are actually buying performance. They're not buying a product and a battery. So we look at it as, what performance do you need for your particular facility? How much demand management and how cost effective is it to get that demand management? So that leads into storage as a solution. It's a solution to a problem. It's not a product. And too many manufacturers now look at it as a product rather than as a solution. Obviously, everyone knows about lithium ion phosphate, LFP. It's the default, but every energy application is unique. And we provide this idea of mass customization where we can actually change both the power and the energy side of the equation. So these are the 8 things that you really want to look at. You're looking at weight. So some applications might need a very, very light product. Some are very safety conscious. Some are power. Some are space. You know, you might have to have a very dense battery if you have very constrained space. So all of these are the variables that you have to manage when you design a system. So we are currently buying lithium titanium oxide from Toshiba in Japan. One of the interesting things about this is LFP has a relatively short lifespan. The Pacific Northwest National Lab and Jamie's group have done a lot of research on actually what the lifetimes of LFP are in the field, and the industry tends to overinflate what they can get 10,000 cycles. They can get 8,000 cycles if you only run the battery at 60% state of charge. So you have to, when you design the system, you're not building a 1 megawatt hour system. You're building a 600 kilowatt hour system. So if you need a megawatt of performance in an hour, you better have a much larger battery than you think you're buying. So one of the things about LTO, lithium titanium oxide, or lithium titaniate, depending upon how you want to talk about it, is it's very highly safe. The design actually prevents internal short circuits, and I'll explain that a little bit, and that is the main cause of fires. We have a very high C rate. We can do, out of the box, our normal design is 2.1 C, which is 4 times greater than lithium ion phosphate. We can do custom up to 4.1 C, and the actual cells themselves are capable of 5 to 10 C. Our cost is higher, but when you have a 20,000 cycle battery overall at full performance, your levelized cost of storage is actually lower in many use cases, and certainly the use cases we are going after. We're actually cheaper on levelized cost of storage, and I have a graphic for that in a bit. So we create tailored solutions precisely sized for each project. Every project is different. Every project gets a different design. The system architecture allows for both AC and DC blocks. And basically, our block, you strictly get it on the site, you put it on the pad, you connect. If you have both a DC connection and an AC connection, you make a total of 2 connections, and it's done. So you just set it up. Very low thermal runaway risk due to the unique battery anode, which is titanium. So it's very good for high-risk applications like urban and life safety environments. We're currently working on New York Fire Department approval for placing large-scale batteries, 1 to 3 megawatt hour batteries in Manhattan, which to date have basically not allowed any batteries in Manhattan because of fire safety. LTO, like I said, is between 18,000 and 20,000 cycles lifetime, and far outperforms LFP technology, where multiple daily cycles are needed. And we very much focused on US-based manufacturing. Other than the cell packs coming from Japan, everything else in our boxes are US-based. Our inverters are coming from the US. Everything else, controls, everything else is US-based. So this is the graphic of what we were talking about the levelized cost of storage. At around 500 cycles per year, which in a lot of applications, especially utilities that have demand charges in both morning and afternoon, or if you're doing solar plus storage integrations. You will have between 400 and 600 cycles per year. And we are cost effective with LFP, even though we cost more on CapEx. And it's a roughly twice on the kilowatt hour basis, though in actual sizing, it ends up being only 20 or 30% more expensive. With the high cycle rates, you end up with a performance adjusted LTO price of lower than LFP. And the tariffs, this chart is a month old, so now with the new Supreme Court, that very top bar will come down a little bit, but not enough to actually be cheaper than us. So this is a little bit technical about the reasons why this is a very safe battery and a very long life battery. So LTO cells do not form an SEI layer, which is solid electrolyte interface. LFP requires that interface to form, and then that actually collects lithium from the electrolyte. And it's because of the electron voltage difference between the anode and the cathode. And if you look at this chart, you'll see three lines, the white lines. And NMC LTO stays within the electrolyte operating window of typical electrolytes. You can actually change electrolytes and minimize some of this, but typical electrolytes, NMC LTO, so we have a NMC cathode and an LTO anode, type anode. And that stays within the operating window, so there is no lithium plating. With LFP, as you get out of that stable window, you actually get lithium plating, which causes dendrites to form over time, and that's what short circuits the batteries, and you get fire. They have done a lot better with LFP over the last few years in tuning electrolytes and tuning the anodes and cathodes, but there's only so much they can do. So this is a graphical image of where we land in the spectrum of batteries. Now, we do have a lower density because we have a smaller band between top end and bottom end of the voltage. We only have 2.7 volts, where LFP is 3.7 volts, and NMC is 4.2 volts. But it's a much safer product and lasts a lot longer. So the key performance characteristics that we tout for our customers, and we basically find products and projects, and we have tons of projects right now. We have a backlog of around 60 megawatt hours in either in engineering, in ready for production, or already quantified of how big the project's going to be. Lifetime and aging, as I said, I talked about that quite a lot, is LTO is a zero stress battery. So there's no expansion and contraction of the anode, which achieves very high cycle lives, exceeding 20,000 full cycles. We tolerate ultra fast charging. I talked about we have 2.1 or 4.1 C, or sorry, 2.4 or 4.1 C, and the cells themselves are capable of between 5C and 10C. Trade-off is energy density, but in stationary storage, energy density is not as much of a problem. Toshiba is coming up with a LTO product that is going to roughly double that watt hours per kilogram. They have them produced now. They haven't commercialized them yet, but they will be commercializing them soon. And this is on the left. The image on the left is the BMU. That's a Toshiba BMU. So they do all of the battery management units for us. And that is a cell pack. That's what we're buying from Japan. and then we put them in racks. You'll notice some unique architecture here is we rely mostly on a passive fire protection, though we do have gas detection. We do not have an active fire suppression. We have firewalls between all of our racks and as well as the top. So we can actually isolate a fire inside a single rack. Our fire simulations right now, yes, Jamie, we will get some batteries up to you. Through those firewalls, it takes 500 hours for the temperature to rise enough to set off another rack, and there's only about 7 hours of fuel in a rack, so there's virtually no risk of fire propagation in the container. This is a really good. I'm going to go over this really quick. 2 charges per day. High variability power conditioning, AI training data centers, I think are a very interesting thing. I'll have some use cases in a little bit where we can be 1/10 the size of an LFP product. Mission critical safety, so think schools. We're putting one of our first batteries on a school, which was hard to convince the community that they wanted a battery next to their middle school. Urban environments, and then market-based is the obvious market-based items. You're looking at congestion pricing, congestion cases where there's interconnection limits for like EV chargers, demand pricing with very high demand charges, or these bifurcated demand network bifurcated morning and afternoon demand charges. Out in Utah at Pacific Core, they have a model like that. So there's some really interesting projects out there. So here's a EV case where there is a constrained interconnection. They're required to have 4 DC fast chargers. And the design was a 1.2 megawatt hour lithium ion phosphate. We could come in and do the same performance with 400 kilowatt hours. So while we were a higher price per kilowatt hour, we actually were $100,000 cheaper. Fortunately, this project didn't happen because it was a NEVI project and NEVI got canceled. National EV charging infrastructure. This is a very interesting one. We're starting to talk to some training data centers where if you read the NERC study on AI training centers and how rapidly they can go from near zero load to near full load within 4 or 5 seconds, that creates amazing, huge stability crisis in, these are 200, 300, 400, 500 megawatt interconnections, and that will destabilize grids very, very quickly. So ERCOT and PJM right now are PJM are starting to look at performance standards for the interconnections for data centers, and it will be very hard for AI training centers to meet those interconnection requirements. And the only way will be actually a change in system architecture for data centers, where they're going to have a single point of common coupling with battery and generation behind it, keeping the inflow from the grid stable. And that will require very, very large batteries that are very, very fast responding. And in this case, a 200 megawatt interconnection we can do for about $25 million with 24 megawatt hours. And to do the LFP version of it, it would be $146 million. So a much, much smaller battery, much higher performance, meets the specs and the performance specs they need. This is a project that we're looking at in Puerto Rico, still in debate. They have the power purchase agreement. Puerto Rico did an interesting thing. They're putting very, very strong ramp rate requirements and grid flexibility requirements and frequency requirements. And to do the same thing with the LFP, they were going to require to balance a 25 megawatt solar project, they were going to need 14.5 megawatt hours of LFP, and we can do the same project with 4, which is a $2.5 million savings. That's us. John Guerin, my chief sales officer, is on the line here. Keith is managing the tech team. And I will go off there. So we are in Lewiston, Maine. Lewiston, Maine is the third largest city in Maine, which isn't saying much. It's about 28,000 people. Old mill town. We are just off the mill area in the DAC zone, so disadvantaged community. We're hoping that half of our workforce will be able to walk to work, many immigrants. We are 5 miles away from an intermodal facility, so we'll be trucking to the intermodal facility and rail delivery all over the US. And we have a container port for European deliveries, roughly 25 miles away, 30 miles away in Portland. And we can be from the container port to container port, we can be in Europe in 8 days.
Thanks, Kay, for that presentation on interesting emerging technology. For more information about the Gridwise Architecture Council, go to our website at gridwiseac.org, and even more important, subscribe to our YouTube channel at the site listed. Thanks.